Hi, everyone. Welcome to our second panel in which we'll be covering 6G technologies. I'm Doug Castor from InterDigital's Wireless Research and Innovation Group, and we'll be moderating today's panel. So when many of us think of the cellular generations, we think about the use cases that are enabled, but behind each of these use cases are novel technologies. 2G, we had mobile voice and the first SMS enabled by digital communications over the 1G analog system. 3G brought data for email and web browsing, which was enabled by, say, high-speed packet access and with hybrid scheduling technologies. 4G brought broadband with mobile video enabled by LTE's all IP network and the ability to aggregate carriers. And of course, for 5G, we've had the triangle of services, which has been enabled by millimeter wave and ultra reliable low latency communications, low latency edge computing, and et cetera. So now that we've heard a lot of the visions for 6G from Mazen Gilbert's keynote this morning and the last panel, we've heard about automation, data-driven networking, drones, et cetera. It's time to start talking about which technologies are going to be enabling 6G. So in this panel, we're going to talk about those technologies, and we're really hoping to cover 4 different areas in our discussions. One, a reflection on 5G, and also, where are some of the highlights, but also some of the shortfalls of we may be seeing for 5G. We'll talk about network technologies, physical layer technologies, and a little bit about the adjacent technologies that are codependent with 6G. So now I'll introduce our 5 panelists and ask that they make a few introductory remarks. Each of them have prepared a few slides to help seed the discussion, and then we'll proceed with a Q&A followed by some questions from the audience as well. So please use the chat window to enter your questions, and we'll be looking at those as we go forward in the discussion. So let me run through our list of experts with the panel. Their complete bios are each very impressive and listed on our website. So after these remarks, then we'll get to the Q&A. We have on the panel today, we have Roger Nichols, who's a 6G program manager from Keysight. Prabhakar Chichapru, who is the head of Small Cell Forum, was with AT&T. Takahiro Nakamura, who is the senior vice president and general manager at NTT Docomo, which is an operator in Japan. Larry Peterson, who's CTO of Open Network Foundation and a computer networking expert. And Muriel Medard, who's a professor at MIT and a physical layer and coding expert. Okay, so now let's get to our opening remarks. Roger, would you like to start off?
Yeah, thanks, Doug. How's my sound? Okay?
That's perfect.
All right, so I appreciate the opportunity. It's an honor and a pleasure. Go ahead and move to the next slide, Doug. One more click after that 6th finger gets added there. Okay, thanks. So I think this morning everybody saw a discussion of market drivers and use models, and also to some extent an introduction to the requirements of the network, and that's on the left side here. The technology enablers come in 5 groups here, and next generation radio, there's a lot of talk about sub-terahertz and maybe visual light communications, but you can expect a lot of work happening at the traditional bands as well, including improvements that will be made in the 5G space in FR2. But then the addition of integrating several complicated radio access technology systems, including a step beyond, release 17 and release 18 for non-terrestrial. Time engineering is a super big deal. That is getting precision and timing in the networks, which is very difficult to do. The optimization of networks through artificial intelligence gets a lot of talk, and then obviously security remains a huge facet and growing as time goes on. So next slide, Doug. So, I represent the part of the industry that worries about design and measurement and validation, optimization. And, we look at this from a slightly different perspective. And I tried to capture some of the things that keep us awake at night when it comes to a brand new set of technologies. And clearly, we have to make measurements and be traceable to standards. That's part of the fundamentals of what we do. And a lot of what we have to do for accuracy and signal processing has an edge to it with respect to metrology. We have to outperform the device under test. But the measurement, validation, optimization, and design capabilities have to extend beyond that physical layer up into the protocol stack, the ability to simulate and design and test that and match the entire workflow, but also a lot of details in each one of those discrete steps. And it's never been more important to be able to simulate and design and then validate the performance of the entire system from an end-to-end perspective. And as the system becomes such that society relies on it even more, there's that much more demand for that capability, which then gets us into quantifying the subjective. That's what I like to say. So quality of service may be pretty easy to quantify. Quality of experience ends up being very subjective and quite challenging. And there's work going on right now to standardize some of that. That will become even more emphasized, and how you measure that becomes a big deal. And then once again, how secure is it? Well, how secure does it need to be? And ensuring that we can measure security also is going to require a lot of work to understand, a wide open environment that is also very subjective. So we're really excited about being part of this. It's a great, yet another opportunity to expand how we enable what happens on a worldwide basis. So looking forward to all this work. That's it.
Okay, thank you, Roger. Had to find my mute button. Okay, Prabhakar, would you like to go with your remarks?
Thanks, Doug. My name is Prabhakar Chitrapu. I'm the chairperson of the Small Cell Forum. And Small Cell Forum addresses all aspects related to small cells and densification in 5G. And then we are also looking at the evolving landscape for 6G and how we can cater to that landscape. Next slide, please. So I thought let's just start at a high level. In any generation, so first of all, we like to think of approach these as generational eras as opposed to just generations, whereby we like to think of at least three components in it: the basic technologies that go into it, then the deployments, and then the services. And the check marks basically indicate that when a generational era launches, the technologies are quite mature, whereas the others are catching up. Next, please. So when you go from one generational era to the next one, next, please. We'll see that the deployments and services will mature completely. And then next, please. And then you basically have new technologies that are being introduced, which is a combination of orthogonally different technologies, and then or the new technologies plus the enhancements to the previous generations. And then of course deployments will follow. So we like to think of it in this three-dimensional landscape. And go to the next slide, please. Okay. So we thought that let's take a quick look at what is the status of 5G, right? And the drivers are several: eMBB, URLLC, massive IoT, densification, and private cellular networks. And each of these is at a different level of maturity as a snapshot of today. And we'll talk more about this in the Q&A perhaps. Next, please. And in terms of the core technologies that are enabling 5G era, this is what I think of as the basic technologies coming from 3GPP, both on the radio side and the core side. And although the standalone deployments are a bit lagging compared to the non-standalone solutions. Next, please. So the auxiliary technologies, as Doug mentioned before, so this is where the era and the 5G kind of make a difference, are distinguished. So here virtualization is a big part of the 5G era. Open networks, edge computing, slicing, sharing of spectrum, and sharing of infrastructure All these are at various stages of maturity at the moment, and as the column on the right hand side indicates. But this is kind of a snapshot of where we are in terms of the 5G era technologies. Next slide, please. So the drivers for 6G era technologies are at a high level. This, first of all, global coverage. Although we have complete coverage in several parts of the world, there is still a 3.5 billion people who are not connected. So I think that will be an important part to address. Demand-driven capacity. Capacity is not uniform everywhere, so you have to have solutions that cater to this. And then advanced network solutions, security, which I'll talk about a little bit more later on. And security, privacy, and trust. Again, a very important aspects. They're getting to be even more important as we move along the current times. Green and sustainable networks. Again, a very important thing. Energy is very important to optimize. New business models. As new players are coming into the field, new business models are important. And finally, and not least at all, I feel that it is time that engineers take ownership of social consciousness and responsibility, because we put our technologies out there, but I think we should also be conscious of how it impacts the society. Next slide, please. Next. So in terms of the ecosystem, so what would be the requirements for 6G? So again, I'll quickly go through this. In terms of the ecosystem, I think having an open ecosystem, multiplayer ecosystem is key. Next, please. In terms of networks, again, this is a big topic in terms of flexible spectrum, multiple access, advanced automation, infrastructure sharing, distributed computing and storage, and so on. These are all going to be very important for the 6G. Next, please. In terms of the core technologies, AI, ML, and convergence of control and communications, and finally, also quantum computing and communications will be important. The last one. In terms of business models, we are seeing that there will be new deployers and new operators for 6G solutions. In addition to the traditional MNOs, neutral hosts, private network operators, enterprise, etc. So all this is very important to consider because they'll generate new business models. And along with it comes flexible service contracts, both at the individual and wholesale level. So all these need to be taken into account. So with that, I want to close and say that I appreciate the opportunity to share some of these thoughts with you all, and look forward to the more detailed Q&A later on. Thank you.
Okay, thank you, Prabhakar. It's great to see setting the stage with the requirements. So next we have Nakamura-san. And we just say in advance, thank you so much for joining us in the late hours in Tokyo. Can you continue with your opening remarks, please?
Yeah, thank you very much for inviting me. Yeah, even though the very late night in Tokyo, I'm very happy to join the 6G event. Thank you very much for your invitation. Okay, so I'd like to explain our views on the 5G evolution and 6G. Currently, yes, this session is just for the 6G, but it is important to consider the 5G evolution also together with 6G. Next, please. This is the requirements for the 6G, and of course, we need to have a much higher performance than 5G. From the left top, extreme high data rate capacity. Yeah, anytime, every generation, we need to achieve the very high data rate, and we set the target data rate more than 100 gigabps. And the extreme coverage, that's maybe big differences from the legacy system, including 5G. We really want to achieve the very, very wide coverage. I mean that the 100% geographical area coverage, and also even on the sea and the sky, even in the space, we need to create our coverage. Maybe 2030s, many people will travel to the space. So it's a chance to have a nice business in the space. and extreme low energy cost. Of course, this is a very important topic. Right hand side, extreme low latency. Maybe less than 1 millisecond latency, low latency will be needed. Of course, this kind of the low latency cannot recognized by human capability, but concerning IoT use cases, things can know the 1 millisecond latency or less than 1 millisecond. So we, for the IoT use cases, we need to achieve the very, very low latency, like less than 1 millisecond. And high reliability also, especially factory use cases, we need to achieve the very, very high reliability. We set the target 7 nines. And the extreme massive connectivity, of course, it's very important for the IoT business. And the sensing is also very interesting topic, and precision positioning is also will be more important for our business. Next, please. Okay, this slide shows how to define the 6G. And in any case, new generation system should have a big gain in performance compared with the legacy system. But what kind of technology can define the new generation system? 1G, 2G, and 3G, the single representative technology could define the generations. For example, 3G WCDMA. But from 4G, multiple technologies, combinations of the multiple technology could define the generation. 4G, OFDM-based MIMO and the turbo coding, IoT and so on, maybe. And even in 5G, more centimeter, millimeter wave technologies, LDPC, polar coding, and so on. Maybe even for the 6G, more combinations of the new technologies can define the 6G, we think. And also in the 5G defined by the ELT plus NR, 5G NR, new radio. What should we do for 6G? Maybe enhanced NR, 5G NR plus future new radio access technologies. Maybe that can be the 6G definition. But maybe we need to discuss more. Next, please. And this is a list of the potential technical components for the 5G evolution and 6G. At this moment, it is a little bit unclear which one is a 5G evolution technology, which one is the 6G technologies. But these are the maybe potential candidates for them. From left, new network topologies, including some kind of the relay or multi-hopping or device to device, more advanced device to device technologies, and so on, to enhance the coverage. And the non-terrestrial network, NTN, this is already treated in the 3GPP, but maybe these technologies will be more important for the 5G evolution or 6G era. And frequency extension controls. Of course, we need to explore the much higher frequency band, like a terahertz level. But considering the realization of the commercialized devices difficulty, maybe our target should be not the terahertz, real terahertz, but up to 300 gigahertz or something like that. And the new radio access technology should be developed, new waveform and so on. And the right-hand side for the enhanced MIMO, massive MIMO, and enhanced URLLC or non-public network that will be continuously enhanced. And AI for everywhere in the mobile network. AI technology can be used for the improve the performance of the radio systems. And also we should consider some kind of integration of the non-cellular technologies, not only the Wi-Fi, but also the Bluetooth or satellite and so on. And finally, advanced network architecture, more flexible architecture, more simple architecture, or such kind of the new network architecture should be considered, considering the variety of the use cases and the very, very high requirements. Okay, that's my presentation, maybe. Next, please. That should be my, okay. Thank you very much for your attention.
All right, thank you, Nakamura-san. Larry, you're up next.
Sure, thank you. So let me take a little bit different tact here. I come from the internet world, the network cloud side of things, and very focused on software at the Open Networking Foundation. We're an open source software nonprofit. And I'm sure you've heard the trope, software eats the network, or the trope that software is eating the world. But I think that that's so true. We can even go so far as to say it's even eating the access network, is maybe the last bastion of non-software penetration in the world. So I'm not sure what mental image you have in mind when you hear about the software eating the net, eating the world, but I want to kind of paint a picture in your mind. So next slide, please, as a way to think about it. I think it's a qualitative change that's coming. This is not just a little bit of technology. So I'm going to look at the 4G to 5G translation and then maybe make a comment about 5G and beyond to 6G. But next slide, please. So standards tell us a lot about how the world is constructed, but it's not the entire story. And as I'm sure we all understand today, a lot of that modularity is packaged up in proprietary bundled devices. Next slide. So what's happening right now is that there's disaggregation going on. And so there's bits and pieces that are being moved out to radio units and distributed units. And I'm sure many of you are familiar with the Open RAN initiative and breaking the RAN into parts. And of course, the mobile core is evolving and it's breaking into parts. And this disaggregation is going to take us to an important place, I think, and it's going to be the transformative aspect of 6G in my mind. So next slide, next overlay. So there's two outcomes of this. One is, first of all, there's a lot of open source here, and that's I think fundamentally a good thing because it's going to open innovation to a much wider audience, and we've seen that open source have a really huge impact in the internet and in the cloud, and I think increasingly that's going to be the case in the access network as well. But it's not just the software is open; it's packaged and deployed and operated as a set of microservices, and that's really critically important because it brings the best practices of the cloud out into the access network. And so, next slide. If there's one thing, sort of mental picture to take away from the message that I have, is that today and historically there has been this dividing line. There's been two parallel universes as far as I'm concerned. One is on one side, the internet now becoming the cloud, and on the other side is the access connected out at the edge. And fundamentally, I think what's happening is that dotted line's moving. Next animation. And I think, yeah, it's moving out to the point that, with the exception that the radio technology, of course, is going to continue to evolve and progress, and it's going to get higher and higher bandwidth. But the access network is essentially going to become an extension of the cloud. I don't necessarily mean that as, it's going to be implemented in the data center. There certainly will be parts of it implemented back in the data center. But the cloud's also moving to the edge, as we know. Edge cloud just means that in close proximity to where those radio towers are, or the small cells, will be bits and pieces of the cloud, and that's where the microservices are going to run. And I'm sure we'll get into this in the discussion, but I think this is going to have a transformative effect on how the technology evolves and changes over time. It's going to become much faster pace. Feature velocity is going to increase dramatically, and I think that's going to have a fundamental impact on what becomes 6G. So I think I'll stop there, and I'm sure we'll get back to some questions around this later on.
Thank you, Larry. Yes, that's definitely a good trend for us to explore some more. Okay, so Muriel, you're next. Maybe muted.
Yes, thank you, Doug. So I'm going to just cover a couple of topics. I'm sure we'll be revisiting these throughout our discussion, and I'm very fortunate to go last because all the themes have already been introduced and very beautifully and ably by all my predecessors in this discussion. I think one of the aspects that really has stood out in what we've heard is the heterogeneity, the fact that we do expect there to be different types of technologies. And I think Larry just alluded to that in terms of having a diversification, ever-growing diversification of access technologies, and the need to make those access technologies in some way virtualized, because I think that's basically really what he's talking about, and that has been indeed the great success, I would say, you know, the genius idea or principle behind cloud services. And so, you know, the image that I have right here is very much in line with what we just heard. We have storage, you know, not just in some you know separated, segregated nodes, but really everywhere, including storage, you know, at the users themselves. We have a high heterogeneity of access, whether it be, you know, a link which is a traditional, let's say, cellular telephony link, whether it's millimeter wave, whether it's a Wi-Fi link, or whether it's actually device to device using Bluetooth or any other kind of short-range technology. So what we have is, in effect, something which is becoming much more difficult to track. Certainly, any idea that relies on having accurate, constant state updates is pretty much doomed, is not going to scale. And so the idea here that we and others have been working on is to use coding. Now, why do we use coding? Coding, of course, is used at a physical layer very actively. I'll talk about that. Sorry, not yet. No, not to the, yes, thank you. I'll talk about that in the next slide, but not yet. And the idea behind coding is really this. It's a synthetic creation of a service, right? So we're used to thinking in the physical layer, I have a channel that's noisy, that's not clean, and I synthetically turn it into a channel that's clean. Here, what we can think of is, for instance, taking a system which is heterogeneous, say having two different links, and creating through coding something which is clean, which is going to give us the type of QoE and QoSs that we want, where we'll be able to trade off throughput and delay. We heard quite a bit, and I wanted to also point out the great presentation by Nakamura-san, also by Roger, about low latency. Latency, which is really traffic in flight, let's call it low delay. You know, the delay and throughput are not inverses of each other. We like to often think of themselves, but as each other as that. But you know, one is the expectation of the inverse, and the other is the inverse of the expectation. They're not the same thing. They're actually things you have to trade off. And coding allows you to prioritize throughput or prioritize delay. And basically, I think that in order to have the sort of really effective virtualization that Larry talked about, and provide the type of quality of experience features that we heard of from the other speakers, we need to have coding. You need to have an active way to integrate these services together. One of the interesting side effects, by the way, is that then you can have, in effect, a very fluid network. You have a fluid network where you're just integrating whatever service, whatever to create a service, whatever resources you have, and you're doing that in a real-time, graceful way, without having to have a huge amount of, again, keeping state and coordination. Sometimes people say, well, you know, if you're really going to be going over a lot of networks, how do you ensure security? And that's something we also heard of from other speakers. Interestingly, if you don't code and you do use more resources, so for instance, you know, you're worried about the reliability of going through a Wi-Fi connection, or you're worried about the vendor for some of your 5G, 6G, whatever G it may be, base station, if you code and you do so correctly, you actually get security. And we have recently shown that with a slight variation on these codes, you get to post-quantum security. So you actually, you know, it's not even in effect a subjective version of security, but it is, you know, one of the strongest versions of security that we can think of right now. So I think that whatever we do, having this sort of integration across the large variety and ever-growing variety of physical access technologies is going to be key. and to have that integration be secure, and to have that integration allow for the synthesis of the type of quality of experience that we want. And in order to do that, we need the physical layer, which now will get us to the second slide. And in the physical layer, what we need is we also need to have more flexibility. And we heard about different codes. We heard about turbo codes. We heard about LDPCs. We heard about Polo codes. And there has been, I would say, if you will, this swoosh, which I like to talk about it in terms of coding. Now, of course, we could all argue over coffee or maybe something more about whether this is the correct taxonomy or the correct time frame. But let's say that it starts with block codes, convolutional codes. So think Reed-Solomon and the such. So-called modern codes in the 90s, such as LDPC turbo codes. I say so-called because LDPCs are actually from the early 60s, rateless codes and network codes, which I just mentioned, and Polo codes, which came about fairly recently and are indeed in the 5G standard. Now, what does engineering need? We heard about it. We need low delay, right? We would like low complexity, of course. We'd like things to be lightweight. We would like flexibility in rate and block length. We want to have that sort of high customizability, the quality of experience that we've heard of from different speakers. And of course, we'd like this to be robust to the physical reality of noise. As we go into more and more challenged areas of the spectrum, the noise is going to get nastier and nastier. And as we have higher and higher utilization of spectrum, that noise is also going to get more structured, more difficult. Now, what is the mathematical model that all of these codes use? Well, except for network codes, because they're not really looking at the physical layer. You use long codes. You basically use averaging arguments. You always have a co-design of the encoder and the decoder. You have constraints which are very severe in length and rate. And I'll show you here, these are some codes over here, the Reed-Muller codes, CA Polar, this is a CRC-aided Polo codes, which are used in the downlink in a control channel in 5GNR, Reed-Solomon and the such. We're looking really at codes that are very, very, very structured, very unflexible. You can do things like puncturing and so on, but it's just a very constrained set of constructions. And on top of that, we introduced interleaving. Never mind the length of the code. We do this averaging to make the noise look independent. And that averaging, we're talking about huge delays. We're talking about factors of 100 or more. The standard IEEE interleaver is interleaving over 100. So, if you're thinking that your code is, thousands of bits long, and on top of that, you're multiplying by 100, we're talking about excessive delays. And in that domain, what we have introduced recently is guessing and random additive noise decoding, which actually forfeits the mathematical model, goes directly to the engineering need. And the idea here is to be able to decode arbitrary codes, so not have to have paired encoder decoders, but to be able to decode by removing the effect of the noise and using the code simply as a hash, as a check of whether the decoding was correct or not. So this work that we've been doing with the Hamilton Institute, we've actually just had a chip that just came out and it works beautifully. But I think this is, again, a direction towards this heterogeneity and this looking at the channels in a new way. And with that, I'll close and give it back to Doug.
Okay, thank you, Muriel. Yes, the coding is certainly a very broad and fundamental piece of any communication generation, so we're glad to have that input. Okay, so I'd like to move on now to some Q&A, which we prepared a couple introductory discussions, and then I also see that there's a lot of questions coming in from our audience as well. So we will try to balance the time there. So the first area I'd like to touch on is a 5G reflection. Really looking back at what has worked well and what some of the shortfalls may be for 5G. And I think it's a very broad question, but I think it's also very important because we're all looking to kind of identify what is that goal that we're reaching for with 6G. So I'd like to start out with Nakamura-san, as a, from the operator perspective. What's working well with 5G, and where do you possibly see some shortfalls?
Okay. Yep. We have already deployed the 5G from March this year. And actually, we started with the sub-6 giga spectrum bands, 3.7 and 4.5. And the 28 gigahertz band just launched several days ago. Yeah. So so far, I see that yeah, sub-6 giga works well, but due to the rather limited spectrum bandwidth compared with the millimeter wave, the performance is a little bit limited, but the coverage point of view, that should be good. Millimeter wave just deployed, so we are not so sure what kind of the coverage could be achieved in the real market. But considering our trials so far, of course, millimeter wave coverage is a little bit limited. And MIMO should be working, yes, very well, but maybe more advanced technique and advanced deployment approach need to be identified, I think. I mean that how to set the antenna, where to set the antenna, and how to realize the small antenna for the easy deployment in the real market, something like that. And also, I really want to improve the performance for the especially coverage for the millimeter wave, and also especially for the uplink performance. Uplink performance should be enhanced because many of the use cases need a uplink, very high data rate uplink. For example, remote control, remote monitoring, everything. The uplink performance should be heavy rather than downlink. So uplink performance need to be improved more and more. And also, of course, the very high requirement, very special requirement need to be met for the private network use cases like a factory use cases, especially factory use cases, very tough. So yeah, so for the private network, especially for such kind of special use cases, we need to consider them.
Okay. Yeah, thank
Special
you.
alignment, yeah.
Prabhakar, do you have comments on this from your experience as an operator?
Yeah, so thanks, Doug. From our experience, I agree that I think with between millimeter wave and sub-6, the challenges are still present. So I think more needs to be done in the millimeter wave area. But I think as I showed in my previous slide, I think the areas where I think 5G has done well is, let's say, the eMBB, the virtualization. A lot of it is already virtualized, and I think edge computing is also getting deployed quite a bit. So I think those are some of the areas where I would say, I think 5G has done pretty well. But there are areas, for example, ultra reliable communications, right? I mean, that has been one of the promises of 5G. I think more needs to be done there. Private cellular networks, I think we have limited, success there. I think there needs to be more done there because, you have multiple, options there. Like a dedicated private network versus, interoperability with the MNO networks, and then so aspects like that. And then I think also network slicing and sharing of infrastructure. I think these, again, we're beginning to see these technologies being deployed and so on. But I think there is a long way to cover here. And in terms of going towards 6G, what I'm really looking forward to is the openness. I think that should be open, and multiplayer systems, I think, should be a lot more developed, and then must become the name generally the norm. I think spectrum agility I think shared spectrum, in the CBR spectrum, I think has been a great pioneering effort, but I think a lot more can be and should be done, and automation. I think that's the other area where I think we kind of see, if you look worldwide, there are some operators where I think they've embraced automation a lot more than many others. And I think this is extremely important, as you go towards the complexity of the 5G, 6G networks. So these are some of the areas I think where, the 6G hopefully will address and improve on the current situation.
All right, thank you. Yeah, I don't know if the other panelists have comments, but I think that the between Prabhakar and Nakamura-san's comments, it really tees up some of the areas that we want to dive into in the next piece of the discussion. So maybe I'll just suggest we kind of move into talking about some of the network technologies and the openness, as Prabhakar had just mentioned, I think is very important. So, so let's turn to network technologies. So I'll direct this first question to Larry then. How might the network architectures change for 6G? When we consider satellites, drones, cell densification. You mentioned Open RAN in your opening statements. So what are your thoughts about the future of network architecture for 6G?
Yeah, thanks. I think the prereq, which is what 5G is getting right, is the disaggregation, that we are able to break monolithic things down into small components, because that is the absolute key to innovation. That I can innovate in a small area that's open and plug that in, and that's proven over and over to be the critical aspect of feature velocity. And I think sort of as architecturally, I would just say what we're doing is we're going to take the architecture of the cloud, which certainly has a lot of IP internet embedded in it, but that's down kind of at the plumbing level. It's really about getting and putting objects using HTTP. That's going to become the dominant edge protocol, I would wager. But in any case, making that available as fundamentally the design and the architecture of the 5G network. So I have the opportunity to customize and personalize much more fine grained than I do now. It's not a one size fits all. You innovate across very narrow spectrums. And, I'm going to predict, it's easy to predict now because 6G is out there a ways, that someone's going to talk about 6G, and it may be tied to the radio technology. But once you get into the kind of feature velocity that's something that the cloud enables, incrementally change just happens very rapidly, and you stop needing or kind of leaning on these generational 10-year markers. If you look at the internet technology, some people say 2.0 and all of that. That's just some terminology that you hang on it. The internet evolved very rapidly and very incrementally, and it continues to evolve. There's new protocols that have low latency, quick, as an alternative to HTTP and over TCP. These are all going to find their way to the very, very edge of the network. And so the simple answer here is that look at the architecture of the cloud and project it out into everything that makes up the access network today.
Okay, thank you. Just pause and see if there's any other comments. You did mention about network protocols, and one of the areas that we talked with some of the panelists beforehand was the new IP, which is from the ITU focus group. I'm curious, do you see that there's a need to do an industrial IP suite, because that's what I understood that was really focused towards, but as part of moving forward to 6G?
Provocative perhaps, but I say no. IP has survived for a long time, and I know it's about latency, but the way you address latency is you move the objects you're operating on closer to where they're being operated on. It's the edge, the cloud moving to the edge is going to be the key. It's not going to be that I have to fix IP so that I can go deeper into the internet. Deeper in the internet is still too far away latency-wise. I am bringing the cloud closer and closer to the edge. That's what addresses latency. Now, you gotta be able to respond very rapidly. I don't think that's a protocol problem. I think that's more how you build objects in the cloud. And certainly the exascale cloud people are really all over the latency and delay issues because they're trying to get as many pages in front of you per second as they possibly can. And low latency in delivering objects off the cloud would, in my view, is going to be far more important than changing IP.
Okay, thank you.
If I may just add to what Larry said, I completely agree with his vision that I think the telecom networks, are and should evolve towards the internet models, where we have seen so much innovation, so much disruption, and so much of scaling, cost benefits. Unfortunately, these have not been, realized in the traditional network architectures and topologies, and definitely looking at. In fact, there are some mobile industry visionaries who said he tells all his people to think of the network as code. Just think of it as code, and that's so. Yeah, I think that mindset has to change within the MNO community. But I think if we really want to reap the benefits of what has been achieved in the data center technology, etc., I think we have to move in that direction to win 6G and even earlier.
Okay, thank you. Are there other comments? Roger,
Doug, I had one wanted to make here. I agree with all of what was stated, with the exception of the challenge of precision and timing. I think we can design systems that are that have a low latency, but the idea of having a precise timing, so maybe not super low in latency, but very exact in terms of when information gets from one place to another. I think that was a big driver behind that new IP discussion in the ITU session. And even in the last ITU meeting I was in, there was a pretty interesting argument against new IP, more from the perspective that it's taken 2 decades to implement IPv6. And so doing a new IP was going to be a big challenge because it's a pretty major overhaul. But that said, I think we have a network architecture challenge in front of us with respect to precise timing. So you have, not just a maximum latency limit, but you might have also a minimum latency limit and a timing that might be, 10 seconds instead of a half a millisecond, but it better arrive within plus or minus 500 microseconds. And I think that's a big challenge for the way that the entire network has been designed so far.
So I wouldn't argue with that. I don't think that's a new IP there. So the technology that sits under IP, which is all of the switches that build out the cloud and the data center today that will build out the cloud at the edge as well. Being able to embed very, very fine-grained measurements and timing in there, which is now starting to happen as networks themselves, as the switches themselves become more programmable, I think is an important technology that could really address that, the accuracy of the timing information.
Okay, thank you, Larry. Yeah, I think the need for the timing accuracy ties back to what we heard from Mazen Gilbert's presentation this morning about the industrial automation as part of the vision going forward to 6G. So that's definitely something that I think that will need to be looked at for the 6G research. Just in the interest of time, why don't we keep moving along, and I want to touch on the physical layer as a next technology area. So, traditionally the PHY has always got the most attention in 2G and 3G, at least. Then in 5G, we had a lot of concerns about reaching the Shannon limit. So we want to look at, where do we go next with the physical layer advances? So let me call on Muriel for this one to, perhaps address some thoughts on, where do we go next with the physical layer for 6G?
Yeah, so I think there's sort of, as I mentioned in my slides, sort of 2 different prongs that I would distinguish there. One is where do we go next in terms of exploiting new areas of spectrum? And we know about exploiting very high frequency areas of spectrum, and also exploiting more aggressively the spectrum that's out there. We heard about MIMO, we heard about cooperative systems. Those are definitely, allowing for much more aggressive, as I said, use of the spectrum that's available. I'd like to put in a few caveats in there, in that cooperative aspects in transmission and reception do come with non-trivial associated costs. So one of the things that we've studied is what we call the cost of cooperation. Having nodes talk to each other to cooperate is not free. And actually, it really does change drastically the scalings that the field had assumed, I would say, until fairly recently. So a lot of potential there, but maybe a more limited potential than what had been up until now assumed. The physical layer, I think, in terms of just the transmission, the spectrum, has to be considered, as I mentioned before, in the context of the ability to access that, right? So it's very related to the discussion that we just had with Larry, because it could be that you have access to a whole lot of physical layer interfaces which are individually not that great. And rather than just choose the best out of a fairly lousy lot, what you would like to do is integrate across all of them. And that doesn't mean switching back and forth like crazy among them. It doesn't mean repeating across them. It means coding across them. So that's one aspect. The second aspect, which is the aspect of, okay, you have a physical layer, you've chosen that, and now you're coding over it, right? Sort of the second prong to the physical layer. And I think that there, what the concentration has been is really on the Shannon limit, as you just mentioned, just getting more and more throughput. And it's a little bit of an odd fixation, because when you look at the efficiency of the overall channel, it's so far below the Shannon limit, it's not even funny, right? Because, okay, maybe your physical layer code does well, and then you have this hybrid ARQ over it, which like adds an extra factor of 3, which is almost like a repetition code. And then on top of your hybrid ARQ, you have an ARQ, and then you have heaven knows what other inefficiencies. So why were you worrying so much about your capacity? And then also, in order to do that, how much have you lengthened the delays? We heard about delays. We heard about delays in the cloud. We heard about going too quick and so on. But the delays that are occurring at the physical layer are themselves getting to be non-trivial, not because the speed of light is low. it's because you have all these extra layers upon layers upon layers upon layers. And certainly, I think that 5G has not done a great job at reducing that number of layers. That has not been something where there's been a simplification. Wi-Fi does tend to have, I would say, more sparse, a more sparse, MAC protocol stack. So, in that respect, I talked about the coding, the noise-centric coding. One of the things that we have found there is like the code doesn't matter, right, by and large. Not only can you use any code that's out there, there's almost no bad codes. Like you can actually use just a systematic code with a few random redundancy bits, and it does as well, often better than the state-of-the-art codes right now. It's about the decoder. It's not about the encoder. And so I think that there then you also don't need to go to these very long codes. You can have very short codes. You don't need to interleave. You can, anything, any structure, any correlation in the noise you're going to be using actively. So I think that really changing how we're looking at the physical layer, and in particular, sometimes not necessarily worrying about Shannon when, I love Shannon, I'm an information theorist, big fan, right? But not really worrying about it when you've got like all these other wasting of resources. I think it's really looking at the whole thing rather than looking at it and just that particular portion of the physical layer. Looking at the entire MAC, I think is going to be crucial going forward.
Okay, yeah. Thank you. I think that's great insight. Look at Shannon from more end to end, and that's great. I do want to touch on just terahertz for a minute. We have another panel tomorrow on terahertz, but it seems like a key topic going forward with 6G. So for any of the panelists, what are the thoughts about the impacts that terahertz may have on 6G, and how close are we in order to be able to realize that?
Yep.
My video is frozen.
Nakamura speaking. Can I speak? Nakamura? Yep.
Yes, please go ahead.
Yeah. Of course, the the terahertz spectrum band very interesting, and operators need more spectrum resources anytime. And but we have not had any good resources in the lower spectrum band. So we need to explore the higher spectrum band, terahertz level, of course. And but unfortunately, we don't have nice devices for the terahertz level spectrum bands. So we need to develop the nice devices, RF devices for the terahertz spectrum band. And also, of course, we need measurement equipment for the very high spectrum band terahertz level. I hope that the Keysight can provide a nice measurement equipment for the terahertz level we needed. So that's a very challenging point to develop the terahertz level system.
Yeah, thanks for the call out, Nakamura-san. So there's, I see the move to new spectrum as inevitable, but terahertz, or maybe what we would call sub-terahertz for now, between maybe 100 and maybe as high as 400 gigahertz. The real challenges are multiple. One of them, as Nakamura said, was devices. The RF semiconductors and the performance of them in that territory is still pretty limited in terms of power outputs and noise performance and that kind of thing. There's a lot of work that has to be done to make improvements there. That's not the only space, you know, even passive devices like switches and filters, you know, things just behave very differently when you get to that small of a wavelength. And then it also implies bandwidths that information bandwidths that we have not had to spend a lot of time on, at least in over-the-air situations. These are bandwidths that are sort of old hat for the coherent optical communicators, the, you know, 20, 30, 40, maybe even 100 gigahertz bandwidths. But in the RF space, it's pretty tough. And the signal processing issues are profound. You know, we've seen sample rate requirements start to get so much higher than clock rate capability in ASICs and FPGAs that the expansion of available resources to do parallel processing means a lot of real serious problems for size and power consumption and that kind of thing. So those are all issues that we have to overcome, both in the network itself and in the test capability that we have to bring forth. We're up for the challenge, but there's a lot of work that has to be done there.
Okay, thanks, Larry. So we have, I think, roughly 10 minutes left, and I do want to get to the audience Q&A because there's a lot of questions coming in. So the panelists should be able to see the audience Q&A that's been sent over to us in the chat window. I'll just go right down the list. So the first one, so there's a question from Leonard Lee of NextCurve. How do you guys see quantum computing communications being applied in the context of 6G? What is the timing of these applications? Prabhakar, do you have thoughts on that, or any of the panelists?
It is non-deterministic. No, yeah, I think, you know, quantums, I think it's still at the technology level, but if you were to sort of think ahead, what comes to mind is actually three things, you know. One is encryption, right? I think it's ideally suited for that. The second would be storage. And, you know, with quantum storage, you can, you know, do massive edge computing, really, you know. And the third one, which is kind of, I find is a little bit interesting. You know, I came across some articles recently about applying blockchain technology to several, you know, mobile network problems. And the point was, you know, as the mobile net systems are getting disaggregated, there are multiple pieces, not only from a network function point of view, but also the players, right? As I mentioned, it's going to be a multiplayer system, which require trust, you know, dynamic trust and relationships and you know, things like that. So they were basically proposing blockchain technology as a way to sort of manage or address some of the heterogeneity and complexity. So I don't have a good feel for it, but something tells me that quantum technology might be actually useful for making blockchain solutions a reality.
If I may add, I like the non-deterministic. I wouldn't necessarily hold my breath for it in terms of an enabling technology, but in terms of a threat, sure, for security, right? So for breaking, I mean, as we know, that since, from my colleague Peter Shor, for instance, RSA is not quantum secure, right? That was one of the things I mentioned in my slides, that we have been looking at using heterogeneity with coding to be quantum secure, because actually the quantum what we call the post-quantum security often right now are actually coding schemes, dating back to Maclise and the such. I think that you can imagine it becoming a threat, I would say, before it becomes a capability.
Okay, thank you. Just moving on to another question. Personalization, how much personalization will be enabled by 6G, enabled in 6G by edge, mobile edge computing, RAN slicing, core slicing, and centralized orchestration? Larry, do you want to take that one?
Yeah, I think that's going to become a really critical part of 5G and beyond that. Both from a resource allocation point of view, slicing that I get some, virtual networks, virtual access with some that meets some QoS parameters. But I think also, maybe even more importantly, from a customization of the service that's delivered. So we've accumulated a lot of standards baggage, let me call it, over the years. Is to be backward compatible, you keep, and as Muriel said, you keep adding layers and layers, and it continues forever because you always want to be backward compatible. But I think there's an opportunity to kind of shed some of that as you customize and you throw up microservices that do 20% of what the full protocol did, because that's the only 20% a particular kind of traffic, a particular application needs. That's all enabled by rapidly deploying customized components, whether you call them VNFs or whatever, in the form of microservices. So that's kind of a well understood approach. And yeah, so I guess the summary is customization. I think more than performance or strict bandwidth is probably going to be the key driver here.
Okay, interesting. Very good. There's another question from, I think there's multiple questions coming in, one from Leonardo, George, and others. What will the role of visible light communications play in 6G? And that's a technology that I found very interesting, and it brings in not only just the physical aspect of getting the communication link, but just the whole systems. How do you develop a system where you're using lighting in a room? Ultra small cells is one way to also look at this. Anybody, Nakamura, or anybody have an opinion on visible light communications?
Yeah, okay. So, of course, it is very interesting topic, and also we need to consider the integration of the multiple access technologies, and of course the visible light communications. That could be the one of them, and but we need to review the real performance and the real use cases, and also cost for the equipment, and business model and so on. So we need to review we need to check the actual, what can I say, feasibility of that kind of technologies for the 6G.
Okay.
I would say just that, again, with respect to all these physical layer technologies that might not by themselves be able to, if you will, carry an entire session, they may be extremely useful in an ancillary way to give, to fill in just a little bit of a gap that there is in the service that's obtained by having a single connection. And you know, when Larry was saying that it's going to be about customization rather than performance, actually I would argue performance is customization. The customization is the performance. So you can imagine, and again, if you have a good way of integrating these technologies, you can now bring in a lot of different technologies without any one of them being able to carry necessarily the bulk of the traffic load.
If
Yeah,
I could,
if I may, I
if I
just want-
could add to that just one thought, which I think that the real sea change here is decoupling technology from the architecture. We've always, each generation has been, because we got some new radio technology, we've got a new generation, we've got a whole new architecture. But I think the secret is that technology can continue to change at the pace it changes. And you've designed a system that new technology seamlessly plugs, a little bit more seamlessly plugs into, rather than having to create an entire new architecture every time the technology changes.
Exactly. And you know, it's not just that you have a whole bunch of different transceivers together, because that's no different. That's not integration, right?
No.
That's just sharing a power strip. It's like I can put my hairdryer and my coffee machine on the same power strip. It doesn't make it a hairdryer and coffee machine. It's really the integration of everything, and not just the proliferation.
Yeah, I just wanted to add to that. Muriel, you mentioned this actually 2 times, I think, this idea, and I completely agree. You know, horizontalization of our solutions has, of course, had a huge benefit, but also people then super focus on each layer in some sense, and then, you know, but every technology hits an S curve, right? So beyond a certain point. And then I think now if you look at it from an overall optimization point of view, it's how you put these together that can actually yield much more benefits. And I think that's where, again, AI tools can come in, because there is a lot of heterogeneity in each of these layers, and combining huge amounts of data of dissimilar nature coming from different layers using AI algorithms can be very, very promising.
Right, as long as, again, you have an underlying technology to unify everything. Because if you have the AI tools to figure out that you have a lot of resources available, and then you don't have a way of actually accessing them together,
Right. Then
yeah, absolutely.
Okay, thank you. There was another question that came in from Hamid Falaki from University of Bristol. I think we've pretty much just addressed some of that by looking at the, you know, how AI optimizes it. But I'm sorry, the question is, please tell us how the distributed ecosystem of functions can be optimized in 6G. So I think that's pretty much been addressed. So let me just go to one very last question, and maybe this can just be answered in a word or two. So with the research timeline for 6G, which 3GPP release do you think will start 6G? So maybe we can just go down the line and get some opinions, and then we'll have to close right after that. Got to be brief, please.
I haven't done the math on it, but I don't expect to see 6G specific in a implementable release in 3GPP until after 2025.
So my answer is it's an irrelevant question. The software will define it, not the standard. The standard is going to be left behind.
+1, Larry.
Nakamura-san, any thoughts?
Yeah,
Okay.
I think that maybe beyond release 18. Release 18 has already started, so maybe release 19 or later.
Yeah, I was going to say the same thing. I don't think anything in 17, 18, it'll be 19 or 20, I think. You know.
Okay. So I think we're just out of time. So, you know, I'd like to close the panel now and just thank all the panelists, and thanks the audience for all the questions. And, you know, I really wish we could continue this great discussion, but we simply don't have any more time. So I hope everyone has found this discussion very useful and another step towards our 6G research.